Yeah, so thanks very much for the invitation, first of all. So, so apologize, I have a slight cold, so I hope my voice will actually survive. So, and I apologize for the coughing in advance. So, and so yeah, so the title is S Constructions, Auslander Algebras and Wrapped Floer Theory. It somehow sounds maybe a bit colorful because it's kind of a mix of a rather diverse range of subjects. And what I'd like to explain is something which grew out of various joint works. The first one is a joint work with, so actually you cannot see. I should probably start by sharing my slides. So there you go. Okay, can you guys see this? Okay, great. Yeah, so it's based on several joint works. First is a joint work with Gustavo Jasso and Tashi Walda, which is published by now. And then there's some work with Gustavo Jasso and Lekili. And so one part of this is published, and the rest, the more recent part, is still in progress. And so what I'd like to explain to you is basically a relation between these various gadgets in mathematics, and I'd like to do that by also just, giving it, because I don't want to assume that you're familiar with any of it. I'd also like to give a quick introduction to each of these. Okay, and so to be honest, our collaborations, they sort of didn't arise from trying to solve some big conjecture or some deep insights, but it was rather just kind of the everyday mathematics you do. You just kind of write a certain kind of diagram. And then you maybe notice, you look at the type of diagrams someone else is drawing, and they sort of look similar. And then you try to make sense of what's behind that. And so the kinds of diagrams that basically the three of us, that was myself, Gustavo Jasso, and maybe Lekili, were drawing, are these three different gadgets. So the first one, presumably everybody is familiar here with. That's what's going to turn out the kind of diagrams that I draw when I build the Waldhausen S-dot construction. The second kind of diagram is, I don't know, maybe slightly less familiar to people here. This is something which originates in the representation theory of finite-dimensional algebras, and it's what is called an Auslander-Reiten quiver, Auslander-Reiten diagram. So we will discuss what this is about. And then there's the last type of diagram, and that's the kind of diagram that you would see if you look at the works of Lekili. So that has to do with a certain kind of categorical Floer theory, wrapped Floer theory, which is captured by the notion of a Fukaya category. And this diagram, as we will see, is exactly such a diagram in a certain example of a Fukaya category. And so now looking at these different diagrams, so they have pretty different meanings in their various subjects. And nevertheless, they pretty much look very similar. And so, so basically what I'd like to explain is a relation, to spell out a relation between these diagrams and what it mediates between these subjects. Okay. And so therefore, what I'd like to discuss now is I'd like to go through the various subjects in which these diagrams arise, then explain the relations among these diagrams, and then I'd like to maybe explain what one could possibly do with it. And so this is a rather somehow new story, I would say. So we probably don't have sort of the deepest applications yet, but I think it's maybe interesting enough to expect that you can make something of it. And so that's what I'd like to tell you about. Okay. And so if you have any questions, by the way, just feel free to shoot in at any point. Okay. And so the starting point is exactly these diagrams of the first kind, which you will find in Waldhausen's construction of algebraic K-theory of spaces specifically. And the special context I would like to focus on here is the situation where C is a stable infinity category. So that's the general context which we would like to work in. or maybe later we will actually specialize to categories that are linear over a field. So think of maybe the derived category of some abelian categories, so something of this sort. And so then the S dot construction is a simplicial object that is built from diagrams of exactly the shape which we see on the left-hand side here. Okay, so what are these diagrams? Well, they're indexed by this poset, so in degree n. They're indexed by the poset just of ordered pairs of numbers that lie in between 0 and n. And these diagrams, they have to satisfy certain conditions. Namely, they're supposed to send degenerates. So what's a degenerate? A degenerate would just be a tuple where both I and j are actually equal. So these guys here would be degenerates on the left-hand side. And so these degenerates are supposed to be sent to 0. And that's the first condition. And then the second condition is that what I write here, what I call rectilinear squares. So everything which kind of is a square with respect to the coordinate axis, the way I drew it here, is supposed to be bicartesian. Yeah, so in other words, what I see here, for example, in this diagram is I see in fact, 4 3-term exact sequences, right? So there's one here, 0, 1, 0, 2, 1, 2, 0, 1, 0, 3, 1, 3, then there's 0, 2, 0, 3, 2, 3, and 1, 2, 1, 3, 2, 3. So that's one way to say this. And so the shapes of these diagrams, it sort of has some interesting meaning also in terms of homological algebra, if you want. So this is a type of diagram you would consider if you try to establish something like the octahedral axiom, for example. So that's why you can think of this, you can choose slightly different coordinates and think of this as a diagram of octahedral shape. I won't do it for you. And then basically the statement is that if you start with the first row, then you can recover the rest of the diagram by forming cofibers. And the interesting content is then that the 3 cofibers you can take, they then again form an exact sequence. So that's it's kind of octahedral diagrams. And then if you increase n, you get higher dimensional versions of these octahedral diagrams. And so the interesting fact, which of course everybody's familiar with here, is that this forms a simplicial object. And so then what's the point of the simplicial object? Well, this simplicial object gives me a way to construct the algebraic K-theory space. Right, so the algebraic K-theory space, as Waldhausen defines it, is then defined as the loop space of, well, where I don't think of this as a category of such diagrams, but I look at the maximal groupoid, so that gives me a simplicial space, and then I just take the geometricalization of the simplicial space, and this then is what is called the algebraic K-theory space. Okay, and so now the question is sort of, or the next step would be to equip this K-theory space with the structure of a spectrum. So we already see it's a one-fold loop space. We would like to realize it as an infinite loop space. And so now there's several ways of doing this. And so the method I would like to present is actually slightly different from Waldhausen's one. And so this is somehow based on the basic insight that if you look at the simplicial object and you just pass to Grothendieck groups level-wise, yeah, so you look at this S dot construction level-wise, then what you actually observe is that this, what you get is now a simplicial abelian group. And so what is the simplicial abelian group? It is actually an Eilenberg-MacLane space, or a simplicial model for it. Of which abelian group? It's just going to be the Grothendieck group of the category C itself, and in dimension 1. Yeah, so this is an Eilenberg-MacLane space. Okay, and so that suggests that the Eilenberg-MacLane space, of course, I can complete to a spectrum by putting this abelian group in higher dimensions and look at the sequence of k pi n's where n increases, and that provides one way to deloop this. But this is in fact, not what Waldhausen does, because what Waldhausen does is he iterates the S construction, and then shows that provides. So you get multi-simplicial objects, and if you realize them, then you get the higher deloopings. So I'd like to now present a way which I'd like to call the higher S construction. And this is inspired, so essentially you can find this maybe in more the context of exact categories, but for d equals to 2 and exact categories, this is actually an approach to d-looping which was taken by Hesselholt and Madsen. And Madsen in their approach to what they call real algebraic K-theory. So that's for real algebraic K-theory. Right, so there you try to construct a Zemo2 equivariant genuine spectrum, and for that purpose, this two-dimensional S construction for d equals to 2, it actually provides a better model, or an adapted model to this question, which then is used in a very elegant way to solve this question in their work. But so this is not what we have in mind. We would just like to increase this d in the sense that we would now like to think of these higher S constructions as categorified versions of these higher Eilenberg-MacLane spaces. And so here's how this goes. So instead of looking at the poset of these pairs, we now look at a poset of these ordered tuples. And so the conditions are more or less the same, sort of the obvious analogs if you want. So first analog is degenerates go to 0. And the second condition is that now rectilinear cubes of a certain dimension go to bicartesian cubes, right? So how do these bicartesian cubes look like in this situation? Well, let me just draw you an example of one of them. So here we have drawing these, right? So we should get a three-dimensional picture because now we have three coordinates as opposed to the 2 coordinates which we drew in the plane here. So, and this is how this looks like. So here I have 0, 2, 2, and then I get 1, 2, 2, and so forth. Yeah, so this cube is supposed to be bicartesian. You can invent a new symbol and draw this in the center here of this cube. And so what does it mean? It just means that this cube here is a colimit cube. So this final vertex here is a colimit of a remaining diagram, or at the same time, that's what bicartesian means, is this initial vertex here is a limit of the cube. And so then you see there's several degenerates, right? So this guy here is actually 0, this guy here is 0, this guy here is 0, and this guy here is 0 in this example of such a cube. And you see that the basic building blocks of these diagrams, instead of these 3-term exact sequences, they will be 4-term exact sequences, where I have this term, this term, this term, this term. And I want to think of this as the infinity categorical, in the infinity categorical context, I want to think of this as an exact sequence with 4 terms, right? So for example, one way to think of this, I could also, so in the initial context, I could start with one arrow and take a cofiber to complete this to an exact sequence. Now here in this context, I would have to start with a 1, 2, 3 term complex. Yeah, so the back face of this cube is a complex. And then this front vertex 1, 2, 3, I can think of as a totalization of this complex. Yeah. And so, of course, you may have seen these kinds of cubes and the kinds of things one can do with them. For example, in Goodwillie calculus, where you play off different types of exactness conditions, where you require that strongly Cartesian cubes go to Cartesian cubes or things like this, right? And strongly Cartesian would mean that all the faces are Cartesian, but that's not what we require here. So here we just require that the whole cube is a limit, respectively, colimit diagram. And then what's the point of this? Well, the point of this is now that this construction actually now provides an alternative way to get the higher deloopings. Of the K-theory spectrum. Yeah, so that's maybe a little less known. So so essentially all the arguments you need, you can, for example, already find in the work of Hesselt and Madsen, all the arguments you need to prove this, and then you need to provide a bit more elaborate versions to make it work for stable infinity categories. But that then can be done. So you can so we can therefore say that these higher dimensional S construction, higher S constructions provide an alternative way to deloop. And sort of the nice thing is that they achieve exactly this goal, if you want, that if I pass to the Grothendieck groups of these guys, so SD.C, then what you recover is exactly these Eilenberg-MacLane spaces, but now in dimension D. Yeah, and so by that I mean just the usual simplicial model, which you construct, for example, via the Dold-Kahn nerve by just placing the abelian group in a single degree and think of it as a single term complex, and then applying the Dold-Kahn correspondence to turn it into a simplicial abelian.
Can I ask a question?
Yes.
So these higher S construction are in this unfinished document by Dyckerhoff and Madsen, right? Is real algebraic theory.
Yes, exactly. It's for abelian or exact categories.
Yeah. No. I wanted to ask if there is a reference that develops them, a finished document that develops them at some point.
Yeah. So I mean, so this statement, I think, so I've been trying to find a student to actually write this. So I don't think this is written sort of formally anywhere. You just have to sort of search between the lines, and then so I don't. This is probably what you mean, right? This statement that you get the deloopings.
Yeah, I would like an actual proof written down.
Yeah, so I mean, so essentially, so the way you can prove it is you can just reprove. I mean, the essential statement in the delooping is additivity, right? And so what you can do is you can reprove additivity for this d-dimensional version. So the fact that it splits semi-orthogonal decompositions. And that proof is just essentially the same, if you want, as the additivity proof, which you usually give. And so this is written, for example, for stable categories. I don't know. I learned this from some lecture notes of Jacob Lurie.
Yeah, I know the proof for stable categories.
Yeah, exactly. And so that if you can just repeat that proof, and then from knowing that, you will be able to.
Only for stable categories, not for Waldhausen categories.
You can also, there's a more general statement. I'm being, for Waldhausen, I would imagine.
I can relax.
Yeah, so I mean, yes, so for abelian categories, actually, like a former student of mine wrote a proof, because essentially what he proved is that you can think of the d-dimensional S construction as some kind of a totalization of the iterated S construction, and that then actually does the job. So then you just directly compare so there's also somehow if you want, I don't know if it's a good news or a bad news, but it produces the same delooping, so it's not yeah. So
no, but I mean, I'm interested for applications to Hermitian K theory, of course, and yeah.
Yeah. Yeah, no, there's no reference. There's no reference I can give you, so, but, yeah.
Thank you.
Okay. Yeah, but actually, so, you know, for example, I was also trying to find like a sort of a simpler proof, actually, a nicer proof than just repeating additivity, but I think, I don't know, there are statements you feel like they should be true, but I was just not able to prove them, so there's certainly, I mean, it would certainly be interesting to clean this up, I think so, but that's not what we're going to discuss today. So, yeah. Okay, so there are already many questions. So, now this, you know, now think of it as like some interesting simplicial construction, and so what we would like to, so and one application is exactly to provide these deloopings of K theory, but somehow, what I'd like to try and convince you today is. There's more structural meaning hidden in these S constructions than, you know, what you need to somehow form their geometric realizations. So, somehow just like there's more you can do with simplicial objects than just realizing topological spaces. For example, you can study infinity categories and things like this. In a similar way, there's a lot of structural things, structural relevance of the cells of this S construction and how they fit together, which goes beyond just producing the K-theory spectrum. So that's somehow the point which I sort of try to make. And doing this sort of in a rather playful way today. Okay, so what I'd like to do now is I'd like to actually move to the second type of diagram, to the second context, and then explain how it relates to these S constructions. And that sort of already goes in this direction. That somehow, this packaging of this homological algebraic information, these kind of diagrams of higher octahedral type, that they somehow encode some interesting algebra. So, okay, and so that's Auslander-Reiten theory. So what is this about? So this will be presumably slightly less familiar now. So this is a certain classical theory actually by now, so which goes back to the 70s. And this is something that Auslander introduced in order to understand the representation theory of finite-dimensional algebras. So let's say, so what is finite representation type? It just means that there's finitely many indecomposable representations, and the typical kind of question you would like to ask is you would like to classify them. Write a list of all of them, write down maybe morphisms between them, and just sort of try to understand this representation theory in some nice way. And so the typical example of these kinds of algebras are, for example, right, so if you take a quiver whose underlying graph is Dinking type, then that would be precisely such an example of an algebra. And so what Auslander discovered is a certain interesting correspondence, which associates to this algebra A another algebra, and this is what is called now the Auslander algebra. And so what is it obtained? It's obtained by looking at the direct sum of all indecomposables. So for each isomorphism class of an indecomposable, you take one representative, and then you take the endomorphisms, and then just, because this is a little nicer, you take the opposite of that endomorphism algebra. So what is the interesting, what is the interesting statement? The interesting statement is, well, you get by this construction, first of all, a certain class of algebras, which are called Auslander algebras. And the idea is now, and I won't be able to really explain this, do this justice in any way. It would take a whole course to somehow really explain this. The idea is now that you get interesting information about the representation theory of this algebra by basically studying, in some sense, this two-dimensional homological algebra of this corresponding Auslander algebra. And, there's this condition here, which is somehow saying that these algebras will always satisfy certain homological constraints having to do with two kinds of dimensions. The global dimension is just a supremum over all projective resolutions, so the lengths of projective resolutions of, let's say, these indecomposables. And then there's a dominant dimension, which I don't think I will even define it because it probably won't mean much to you. In any case, there's some homological constraint which you can make, and that characterizes precisely this collection of algebras. Okay, and so now somehow the point of Auslander-Reiten theory is to study, as I said, the representation theory of A via using this functor, which somehow takes this guy here, let's say the sum of these indecomposables, let's call this n, and then we get a functor, of course, by Homing out of n from A modules to gamma modules, and one somehow tries to understand things about the representation theory of A via this process. Let me give you an example. And what's this example? This is easy kind of a Dinkin type quiver. It's an A3 quiver. And so let's try to understand what the corresponding Auslander algebra is, right? So for that, I have to understand what are the indecomposable modules. So here's a picture of them. So you just label them by basically labeling the simples that appear in the decomposition series, or in other words, you could also think of just labeling the dimension vectors. So there's this 3 here signifies the representation with dimension vector 0, 0, 1, and so forth. And so this is a collection of all the indecomposables of this quiver. And so you see there are certain morphisms relating them. So that's what I drew in this quiver diagram here. And then there's certain zero relations. So for example, the composite 3 to 3, 2 to 2 is 0, and so forth. And then there's also certain exactness relations, actually. Namely, the sequence 3, 2, 3, 2 is exact. Yeah, and I could remember that, actually, by forming some, not just the plane endomorphisms, but I could form some X algebra with some A infinity structures and so on. And if I did that, then modules over this derived endomorphism algebra, they would just be Morita equivalent to modules over A. But that's not what I'm doing. I'm deliberately discarding information. And so I'm forgetting, for example, that these sequences here are exact. And so the corresponding algebra is now really just the endomorphisms. So if you want, it's the path algebra of this quiver whose shape you see here. Yeah, so now you just ignore the fact that, that these actually had some meanings, and you just relabel them 5, 6. So you get a quiver with 6 vertices, arrows as indicated, some relations, and the path algebra of that modulo the relations will be exactly this, this algebra gamma. Okay. So now this, of course, recovers exactly this diagram too here, and you already see that this diagram, well, it has exactly the shape of this cell, which is captured by the S construction. So we already see this relation here. So what I'd now like to explain is that, in fact, there is a higher dimensional version. Just like there is a higher dimensional S construction, there's a higher dimensional version of these Auslander algebras, and they somehow nicely correspond to these higher dimensional S constructions. And so here's how this goes. So this is what is called the higher Auslander correspondence. And so this was introduced by Iyama. And so, for example, one nice place you can read about this is his ICM address in 2018. And so he basically just asked or answered the question, how can I increase the dimension here? So I just replaced the 2 by dimension d plus 1. And so what I get is another class of finite-dimensional K algebras satisfying precisely this same homological constraint. And so the question is then obviously what's supposed to be on the left-hand side. Yeah, and then it turns out that it's not just a finite-dimensional algebra. And typically these won't be a finite representation type. But what happens rather is that there is a certain choice of a so-called cluster tilting module, which collects not all of the indecomposables, but it carefully singles out a certain class of indecomposables which satisfy again some nice homological constraint. And what's this homological constraint? That homological constraint, so what is a D-cluster tilting module? That's saying that these are maximal with respect to a certain condition, namely there's not supposed to be any self-exts for 0 less than I less than D. Okay, so maximal in the sense that if you can find any indecomposable such that if you add this indecomposable to n and it still satisfies x I is equal to 0 in this range, then it must already be a summand. So it's maximal in that sense. Okay, so somehow, for example, if you take the additive hull of this module n here, then somehow you get some category in which there is only x's that are multiples of this dimension d. So it's some kind of a sort of version of homological algebra, version of an abelian category, which skips these intermediate extensions and only thinks of these xd's and powers of that. You know, and maybe you already see that this seems actually a little bit like this here, where we only think of these 4-term exact sequences and we don't see any 3-term exact sequences. So this sort of already hints in exactly this direction, and we will make this precise. So what's a...
Can I just ask
yeah?
Sorry, so you said that there's no x up to dimension d in the definition, but did you also say that all the x are in multiples of d? Is that?
Yeah, well, yeah, so I said that if you... yeah, exactly. So I say that this will happen if you actually now take the additive hull, so the additive closure of exactly these guys in. Yeah, so you take summons in that, and you take and so forth. So then you get what is called a d-abelian category. So yeah, but so for now, this this we will only focus on exactly this n here. Yeah? And so then what we do here is we do exactly the same kind of construction. We take endomorphisms of this guy n, so forth. Okay, and so what is a good example? So just bear with me a little bit. I understand that this is sort of this is not making any detailed sense, but I hope that it will maybe make sense once we connect to the S construction, because that will bring us back into familiar territory and tell us something maybe about some intrinsic meaning of these kinds of conditions. So one example, which is an example which was actually introduced by Iyama. So here, this is an example which was introduced by Iyama himself, is the following. And that's a statement that I can actually iterate on the process that we have started here. So I start with the algebra A, which is a path algebra of this quiver. Then I look at the corresponding Auslander algebra, which is the path algebra of this quiver with relations. And then it turns out inside the category of gamma, so gamma itself is actually an example of such an algebra which will now turn out to have a 2-cluster tilting module. So I can iterate. I can again take endomorphisms of this guy, and I get some sort of higher dimensional versions of the AN quiver, which, you know, for a fixed D will have homological dimension D as opposed to homological dimension 1. Yeah, so in the interesting situation, this global dimensional dominant dimension will actually always equal D plus 1. And therefore, what we produce is certain examples of homologically higher dimensional algebras, which are interesting. Okay, so this is an interesting class of examples, therefore. And so these are called higher Auslander algebras of type A, of Dynkin type A. Okay. And so what's the point? The point is, so that's the first theorem, is that in fact, so we will explain this in a little more detail. Actually, if you look at perfect modules, so representations of this d-dimensional Auslander algebra of type A, then that is actually the same thing as looking at the n cell of the S construction in dimension D, if you evaluate it in the category of perfect complexes. Okay, so, and how does, let me just tell you how the proof goes maybe. So here's, which also gives maybe more meaning to this equivalence here. And so here's how this goes. Here's a diagrammatic shape which labels a cell, a 4-dimensional cell of the 2-dimensional S construction. Yeah, so this is how it looks like. And now if you think of here, let's just label the non-degenerate ones here. So right, so this is how this looks like. Here are non-degenerates. Here's a non-degenerate. Here's one. Here's one. Here's one. Here's one. Okay. Now here, what I drew for you is just, I iterated this construction one more time. Okay, so this guy gamma here is with respect to our new notation, this guy gamma here was actually equal to A3 and then the 2-dimensional version. And so now what I have done is I have looked at modules over this guy with respect to exactly these labels here. And these are in fact all the indecomposable modules you can now write for this algebra A32. Now the claim was that inside this algebra A32, or inside this module category, there's a certain two-cluster tilting module, which collects not all the indecomposables, but it carefully singles out a certain collection of indecomposables, such that if I then take endomorphisms, I go to the next level here. And now what turns out to be the case, well, what are these? Oops, these are precisely, let's label them here. It's precisely this guy, this guy, this guy. Then I have this guy, this guy, this guy, this guy, this guy, this guy, this guy. So the ones labeled in orange, if you take the direct sum over them, these are exactly the two cluster tilting module. And now, you know, what you see is that there is actually what exactly these modules here comprise. If you unravel, you know, what exactly the commutativity relations and the zero relations and so forth are, and the exactness relation also in particular, you will find that this two-cluster tilting module, it forms precisely a diagram of exactly this shape S4. So in other words, inside, if you want, perfect modules over A32, I find an example, I can write down some kind of canonical example of such a Waldhausen diagram in dimension 2. And in fact, it's not just an arbitrary, that's exactly what this theorem here is saying. This is not an arbitrary Waldhausen diagram, but it's the universal Waldhausen diagram. This is a universal S24 diagram. Yeah, in the sense that, right, for example, the way I formulated it here is writing down a Waldhausen diagram valued in perfect complexes over K is the same thing as writing a representation of A32, which is perfect. Yeah, in the sense that this is a universal diagram. If I have such a module, I just pull it back, and that way I can write down any Waldhausen diagram of exactly this dimension. Yeah, so in other words, these higher dimensional, higher Auslander algebras, they have a universal property. Namely, they're a habitat for the universal Waldhausen diagram of this higher dimension. And that, you know, is just what you can prove in all dimensions. And it's basically amounts to understanding the combinatorics of these cluster tilting guys and then just writing this diagram here. Okay. Yeah, so this was now a connection to representation theory, and maybe I don't want to elaborate on that too much. So what we have done so far is we have, for example, explored how certain things that representation theorists are interested in this context, such as tilting theory. So you certain changes of coordinates between certain submodules of these cluster tilting modules. And so the kinds of statements we've explored is how to relate this to some simplicial combinatorics that has to do with the cells of these S constructions. So that relates to some categorified Horn filling conditions and things like this. And so this is the types of things that we've explored there. But rather than elaborating on this, I'd like to move on to explaining the other relation, namely to this symplectic geometry. But maybe let's see if there's some questions. Okay. Yeah. So what's the second connection, or a third? So yeah, second connection between the S construction and some structures. This would be structures in symplectic geometry. And here I will even have less time to explain this in detail. But again, there will be a statement of this kind. That somehow the categories we produce are universal examples that are a habitat for these S construction diagrams, and maybe that will sort of have to be sufficient to serve as give us some intuition. And so this will now be the third part here. And so what is this? Well, this is a certain part of symplectic geometry, which if you want is a categorification of relative homology in some sense, so in this kind of a situation. So what we look at here is we look at the unit disk in the complex plane, and what we're drawing here are we could think of them first of all as relative first homology classes. That's one way I could think of this, relative to these boundary components, which are separated out by specifying the roots of unity in the boundary of this disk. And so then what these categorical structures amount to, which are called Fukaya categories, are certain categorifications of this, where instead of having relative homology classes, these arcs here, so these are now think of as Lagrangian submanifolds, and so these become objects of a certain category. And so categories are elaborate to build, but in this case, in these examples, they turn out to be of a purely combinatorial nature. So in general, you will have to choose all kinds of auxiliary data, and then you have to compute the morphisms between these objects by some Lagrangian Floer homology. So it's an elaborate process, and the kinds of categories which you arrive in this situation here are what are called partially wrapped Fukaya categories. Okay, and so again, what will turn out to be the case, so you will already see here is there's this index ij, which relates to precisely this index, these indices which I have drawn here. So again, inside these categories, you will see a universal shape of exactly this kind. Now the question is, this is what we've been exploring mostly in recent times, is what about higher dimensions? So how can we see these higher dimensions, higher dimensional S constructions in the context of this type of symplectic geometry? And so here's how this goes. To higher dimensions, it turns out you get by looking at symmetric products. Yeah, so the symmetric product of the disk, that's that is in this case just going to be a ball, right? Inside d-dimensional complex space. For example, you can realize this by using elementary symmetric, using the elementary symmetric polynomials as coordinates. But then what's going to be interesting is that there's a certain collection of stops here, the boundary. And so, so this is again going to be a partially wrapped Fukaya category. Where there's a certain collection of stops. And so what are these stops? So the stops actually already appear in the first example. So there's some issue when you define these Lagrangian Floer complexes because you want them to be invariant under Hamiltonian isotopy. If you then look at non-compact Lagrangians, then there's a problem at the boundary. And so what you do is you use a certain especially constructed Hamiltonian, which which in a typical situation will wrap the Lagrangian around the boundary component. And so this is what is called wrapped Fukaya category. And partially is because this wrapping will stop whenever there is a divisor, which is called a stop. And so here in this situation will be these points, which are these divisors. And in higher dimensions, I can think of the points of the symmetric product as divisors of degree d. And so then the stops are just going to be the loci where one of these where one component of this divisor is actually lying inside the original stops mu n plus 1. So anyway, so it's some category, and so what's interesting is that these objects, they can be labeled by taking products of Lagrangians in these original guys, such that the Lagrangians don't intersect, and so henceforth they define Lagrangians in the symmetric product. Okay. And then there is certain grading data, which I have to choose. So what's the theorem? Again, this category, which is now built from using this symplectic geometry, it is also a universal recipient, so to say, of exactly such a higher dimensional S construction diagram. And so how does this go? Well, let's see, right? So what I'm claiming is that I can write down exactly a diagram of exactly this kind, where I can find an S construction diagram inside this Fukaya category. And so let me just tell you what it does on objects. On objects, it just takes I less equal j less equal k. So let's say we do this in dimension 2 again, right? So in dimension d is equal to 2, it takes this guy here, and what does it assign it to? It assigns it to a product Lagrangian, which is Lij times Lik. Okay, so without knowing what this category is, you can just think of it in terms of the S construction. So in other words, it's just a way of thinking of the S construction, or this cell of the S construction, thinking of this in a geometric way in terms of these product Lagrangians in the disk, which I think of as defining Lagrangians in the symmetric product. Okay. And so this was this third connection. And now the question is, so now we have these relations between this, let's say, simplicial combinatorics that on the one hand serves to define algebraic K-theory and its delooping. And now we have these more structured interpretations where these diagrams actually label certain interesting objects in geometrically defined categories. And so now the question is somehow what can we do to build on this? Okay, so let me give you one example of how we can now, we now just look at what are people interested in maybe in one of these fields, and let's see what we can learn about this by looking at it from another perspective. So let's just think of it in these playful terms. And so here's one interesting observation, which has to do with the combinatorics of these higher dimensional S constructions. And this I'd like to call categorified binomial duality. So what we realize, and we can prove this, essentially in three different ways, because we have the equivalences between these three different categories: cell of the S construction, higher Auslander algebra, or this Fukaya category. So everybody will have their favorite way of proving this statement. For example, as a K-theorist, you would probably use some version of additivity with respect to certain semi-orthogonal decompositions of these higher dimensional S constructions you can write down, and then you just use that K0 splits that. And then you would easily convince yourself that, that the rank of the Grothendieck group is exactly this binomial coefficient, which, of course, as we may remember, satisfies the symmetry here. And so that raises the question if maybe this binomial duality here, it actually can be lifted to a categorical level. So are maybe the cells of these S constructions or these wrapped Fukaya categories also going to be equivalent? And now this is a statement which, at least to a symplectic geometer, it comes as a rather big surprise, because these are symplectic manifolds which are going to be of a different dimension. Yeah, so I take sim n minus d and I take sim d, and there's sort of not really any reason to expect maybe a priori that they're equivalent. But then once you start thinking about it, it's actually a really nice symplectic proof you can give about it. But what I should say is that this statement, as it stands, formulated in terms of the S construction in higher dimensions, it is actually the main result of a recent PhD thesis of Beckert, who actually spent quite an elaborate effort. And he essentially used the simplicial combinatorics of these higher dimensional S constructions, translated that into the language of derivators, and then it took like something between 50 and 100 pages to unravel the combinatorics, which you need to get from here to here. So this is really some rather non-trivial equivalence. Okay, and so symplectically, now it turns out you can see this rather nicely, directly. But we should also say that we're using some rather strong results here. But still, it kind of gives a rather appealing picture to sort of the reason of why such a duality would be true. Okay, and so here's the reason. So the reason is somehow, right? What is this? What does this binomial duality materialize to? It somehow has to do with looking at one subset of cardinality D, or looking at the collection of subsets of cardinality D of the set, let's say 1 through n, and then switching to the complement. So somehow the different interpretations of this binomial coefficients, they materialize to switching from a subset of cardinality D to the complement, which will have cardinality n minus D. And of course, there's as many of each class. And so that materializes this bijection here. And so it turns out that exactly this materialization, it can be translated into an equivalence between these categories. And how does it go? Well, I take one such a set, and now I have to map it to a Lagrangian in sim D. So how does it look like? So that's going to be a product. That's going to have to be a product of D Lagrangians. And so the product I'm choosing is exactly what we call the standard generators, L0I. Yeah, so it turns out the collection of these Lagrangians, it generates this category. And then you just compute the endomorphism algebra of exactly these Lagrangians, and you will get a rather easy description in terms of this algebra here with some relation modded out. So it's the poset, in other words, of these subsets with some relation modded out. But then at the same time, I can think of this subset I in terms of its complement, and I can form another product Lagrangian here. But here I now take a different one. So here I take J is not in I, and then I take the Lagrangians Lj minus 1j. Okay, so it's different types of Lagrangians. Here I've used these Lagrangians which start at 0 and then end at one of the other segments, and then I've taken all possible products of those. And here I've taken these sort of, we think of them as causal dual Lagrangians, which stretch from one segment to the next. And it turns out that the algebra, they span in this category respectively and in this category respectively are just the same. And so that gives a proof. So in other words, it's a change of coordinates from this collection of generators to this collection of generators. So I find a rather appealing geometric way of explaining this, which avoids tracing through some rather elaborate combinatorics here. And so I should maybe say, so what goes into this is a statement which is called Oru generation. So Oru studied these categories and analyzed them. And this is heavily based on his results. And this is also ICM. So it's a nice ICM article. It's ICM 2010. If you want to read about this, this is exactly what you will need to finish the conclusion of this proof. You will have to read his address, which you should do anyway, because it's very nicely written. And then it also, so his discussion is actually based on a specific way of computing morphisms in these Fukaya categories, and that relates to what are called strand algebras, which is the computational device you then use to actually verify that this is precisely the kind of algebra you get. And this was done by Lipschitz, Oswald, and Thurston in the context of Heegard-Floer theory. Anyway, so this is a kind of maybe joyful way of kind of trying to mediate techniques from one of these subjects to the other to learn something about it. So what are we mainly interested in? And so the most serious application which we would like to have is actually the following: is after having an understanding that these rather simple combinatorial examples of Fukaya categories associated to these symmetric powers of disks are captured by the combinatorics of these higher dimensional S constructions. What we would now like to do is to exploit this and use the relation between these various cells given by, for example, the simplicial structure and possibly other functorialities, additional symmetries, and so forth. We would now like to build on that to actually define these Fukaya categories in greater generality. Okay, how is this supposed to work, or why is it supposed to work? Well, this is another way of thinking of this as a process of categorification, and that's categorified cohomology. Namely, another way to think of these Grothendieck groups of these wrapped categories is that they actually, I can think of them as this abelian group as a certain cohomology group with support. That's the way. So there's several ways to think of it: either homology, cohomology, and I can somehow naturally relate to either. So here I would like to think of them, of this abelian group, as cohomology of the disk And so this d power now always means the symmetric dth power. So it's the cohomology of a disk in the middle dimension. Yeah, that's where the Lagrangians are supposed to lie to. So in the middle dimension, and it's supported at exactly the symmetric power of such a graph, which I've embedded inside here. Okay, so this is just something you can compute. And now, on the level of cohomology, there's a question, how can I now use these guys here, these local cohomologies, as building blocks to compute some more interesting cohomology groups? Okay, and so one interesting cohomology group you can compute is you can look at now a Riemann surface, yeah, possibly with some boundary components, some holes, and then there could also be some of these, which I think in Fukaya terms as stops. There are just certain marked points on the boundary, and now I choose some graph which is embedded in this surface. And now I can ask exactly the same question. I can compute the dth cohomology with support on the dth symmetric power of this graph in the dth symmetric power of the surface. And so that's, already maybe a rather interesting topological space. And now I can compute this. The way I can compute local cohomology is I can first localize the cohomology along this graph, or the symmetric power of this graph. So that guy here, it forms now a constructible sheaf. Yeah, so this guy will be a constructible sheaf. And the stocks, will be built from exactly these local pieces. Yeah, so how will they look like? At a divisor which has certain multiplicities, it will look exactly somehow like this, n1. I don't know, my time is getting less, so let me just sketch this here. It's going to be basically tensor products of these kinds of local cohomology groups. Yeah, and it just comes from the fact, right? What does this stock correspond to? It's any point in the symmetric product. You can think of a divisor. So it's a linear combination of points. Let's say this point, this point, this point, and this point. And each of these points has a multiplicity. Let's say multiplicity n1, n2, or no, not n1, but rather d1, d1, d2, d3. It's all these multiplicities. And depending on what the multiplicity is, I take the respective symmetric power, and then I compute exactly the local cohomology, and the rest is going to be a product of all these contributions, and that's going to boil down to this tensor product. Anyway, so that's by the way, it's a constructible sheaf with stocks, and it's a constructible sheaf of abelian groups. Yeah, and then if I compute the global sections of this, I get the global cohomology with support, and that's a way of computing this global cohomology in terms of local contributions, which are exactly these local pieces. And now the question that we're after, and that's the work which is still in progress in its technical details. It's somehow clear that it will work, but the technical details are surprisingly subtle. What we'd now like to provide is a lift of this local system valued in abelian groups to a local system valued in stable infinity categories, whose stocks are, well, precisely these, not just these Grothendieck groups of these S constructions, but the stocks are supposed to be precisely tensor products of exactly these higher dimensional S constructions. K and K. Okay. And so this we would like to do, and the reason why this is interesting is because what you can then check, it's somehow rather clear, modulo some coherence questions, is that that this construction here, it's actually independent. It's independent of the choice of this y But in fact, it only depends on the surface together with these points where we have chosen this lambda here, where we've chosen to terminate. And so therefore, what we hope is that this actually provides an intrinsic alternative definition of Fukaya categories. At least of these types that we have seen here, which is based on, or let's say as, thinking of these as categorified, as a categorified version of cohomology, which is based on exactly the cells of these higher dimensional S constructions, and possibly some variants of that. Okay, so now I think I'll have to conclude because my time is over. Sorry for going over time, but this maybe as a final word, this is what we have in mind when we say that we think that the S construction, it sort of hides more kinds of things that I can do with it, which go beyond just using it as a way to deloop K-theory, because it has all these structural meanings in this kind of combinatorial symplectic geometry, and we hope to exploit this to actually provide an intrinsic account of this combinatorial symplectic geometry based on the types of simplicial structures that you are used to from working with algebraic K-theory. So thanks very much.
Yeah, thanks a lot for the talk. So are there any questions?
I have a question. Is there a connection with two-signal theory here?
Yes. So there is a connection, and so the connection with two-signal theory. So there's one connection, which I somehow always thought is going to be relevant to do something of this kind, and maybe it will be at some point relevant, but it's until this day we haven't found any application of just this phenomenon. And so what we have is that these d-dimensional S constructions. So these are examples of 2D Siegel spaces. So, in other words, just like, so you refer to the two Siegel conditions, so they amount to saying that the one-dimensional S construction satisfies a certain descent condition with respect to triangulations of cyclic polytopes, of just polygons in the plane of convex polygons, and so these higher dimensional versions, they will satisfy higher dimensional versions of these descent conditions that have to do with cyclic polytopes, but now in dimension 2D. And so the condition is exactly the same. It's the condition that whenever you write down a triangulation of such a cyclic polytope, then that will provide for you a certain kind of membrane built out of subsimplices inside a big N simplex. And then the statement is that you can recover the cell of the S construction as a fiber product, as a homotopy limit, if you want, over the simplices that are part of this membrane corresponding to the triangulation. So there's a higher dimensional version of that, and that's one connection. But actually, it turns out that if you want to do, right, so the two Siegel condition in this question here. So this question in dimension 1, it is completely solved, like in many different ways. So this was maybe, so this whole subject of trying to compute Fukaya categories that way, I should say, by the way, was initiated by Kontsevich, And so in this instance where d is equal to 1, so that's just the surface itself and no symmetric power. So in this dimension, that has been worked out by now in from many different perspectives by many different people. So there's work by Nadler, many other people. I myself, with Kapranov, have provided some approach to this. And in this approach, with Kapranov, the independence of the choice of this spanning ribbon graph here, this precisely amounts to the two-Siegel condition. So this, in dimension 1, this is precisely the two-Siegel condition. In higher dimensions, as I told you, it's also independent of this choice. But that has to do with a more complicated condition that involves a certain formula which builds an n-dimensional cell of the d-dimensional S construction in terms of a fiber product that involves tensor products of lower dimensional S constructions. And so there is sort of a version of these descent conditions, but it's maybe a little less obvious generalization, I would say, than the two-Siegel condition, than the one you would sort of imagine from the two-Siegel condition.
Thank you.
Yeah, there's Ezra.
Yeah, cool. I was just on the second last page, on the left page that you have displayed there, on page 11. This is a random thought, but in some of the work on presentations for mapping class groups, there's a sort of principle that you can restrict attention to configurations of loops which form a Coxeter diagram, in fact, simply laced Coxeter diagram. For example, the E6 diagram comes up in genus 3 and somehow plays a big role, even in all higher genus. I was wondering if there's anything like that going on here, conceivably.
So, I mean, so I don't know if it relates exactly to these kind of configurations, but I mean, so there are statements of this type which are generation statements, right? That somehow, in order to generate the Fukaya category, you don't have to write down all the Lagrangians, but there's a certain subclass which you can write down, and then there's different collections of generators. And Uru has proven this a result which is sort of as beautiful as it can be. It's basically saying that whenever you draw some Lagrangians on the surface that subdivide the surface into disks, where each disk contains exactly one of these stops, then that actually forms a collection of generators. So you can therefore describe the whole Fukaya category as the derived endomorphisms of the sum of these objects. And so that, I don't know, so that may possibly relate to that. I'm not totally familiar with these types of configurations you're talking about, but it would be interesting to see if that is the case. So
It has some sort of relation, sort of on braid groups of monodromies or something.
yeah,
Playing a role.
right. Yeah. So these, of course, the mapping class group will then, act on. I mean, that's sort of one point of trying to do this. Actually, of trying to complete this program here is once you have completed this, you could do this actually not just over a field, for example, but you could do this over the sphere spectrum just in the context of stable categories, and you will automatically, for example, let's say you just specialize to a punctured disk. On that, you have the braid group action by the mapping class group, and you will see this in a coherent fashion. So you can, that's sort of one of the future directions that there's a strong potential of using this actually to construct things like knot invariants based on exactly these mapping class group actions. So that's certainly in the picture, and you will get this more or less for free. These braid group actions and mapping class group actions after you have spelled out this coefficient system here.
Actually, I had a question, a general question. I was wondering, so, I mean, do these connections between, like, these, these higher dimensionalized constructions, or more geometric constructions, I mean, do they also lead to various additional symmetries on K-theory? I mean, like this rotation invariance.
Yeah, so I think I'm not sure to which extent they will be new, but so there is certainly, so if you, yeah, so that's an interesting question. So so there is, so let's see here. I mean, like in this shape here, you just like, so basically to see the paracyclic symmetry on, let's say, this guy here, right? You sort of need to make yourself more room and introduce even more redundancies by completing this picture to add even more objects, right? So you would add an object here, which will then be, let's say star means a 0 object. And then you just keep pushing this out. So you get this kind of a shape which you can then actually shift toward in either of these diagonal directions, and that will then provide for you this paracyclic symmetry. And you can do exactly the same thing in these higher dimensional versions, where it's just a 3-dimensional version. You just keep sort of packing these cubes sort of next to one another in some sort of a snaky way. And then you can again shift across the 3-dimensional diagonal, basically just shifting all the indices simultaneously. And that also equips these guys with a paracyclic symmetry. And yeah, so I'm not sure if this, so it's a great question. Yeah, so I don't know. So I was meaning to explore this corner from a slightly different angle, and that's certainly a good question to keep in mind. So there's also some examples where you have this paracyclic symmetries on relative versions of the S construction of Waldhausen, and that's, I think, certainly interesting to understand then what this means in terms of rotational invariance as spelled out by Jacob. But this, yeah, I'm not sure if this will give anything new. So it's interesting. Yeah, I don't know. It's a good question. It somehow should have to do, right? So basically the fact that K-theory has this rotational symmetry, it boils down to the fact that shifting by 2, sort of the most down-to-earth version is that shifting by 2 has no effect on a K-theory class, right? And there's certainly versions of this kind here where you shift probably maybe by 2D or something like this. But I'm not sure if that's then something new or if it's already somehow encoded by this other rotational symmetry, because it's a multiple of 2. So I don't know. So it's an interesting question.
Thanks. Yeah. Oh, wait, sorry. There are a couple of questions in the chat.
Yeah. So there's one. Is it conceivable that the higher Auslander algebras of type D have a K-theoretic interpretation? I think totally. So I don't have a direct answer, but so since Dan Grayson was around earlier, I'm not sure if he's still around. So if you just look at not the higher versions of the Auslander algebras, but just the diagrams of type D. So in other words, you look at, right, so the S construction is basically looking at sequence of representations of the AN quiver where N increases, because up to forming these pushouts, that's all that's contained in each of the cells. And so if you do the same thing for the DN quivers, then you also actually get a simplicial object. And that turns out to be what is called the Gillett-Grayson construction, which somehow is a, how to say, so it's a way to take the loop space already on the level of simplicial objects. So if you take the geometric realization of that deconstruction, or deconstruction that is called, I think, right? So if you take its geometric realization, you get the K-theory directly, and you don't have to take loops. Right, and their motivation is, of course, was to understand like polynomial functors and so forth, which you cannot hope to construct after de-looping because they're not additive. So therefore, I haven't thought about this, but I would imagine that the higher dimensional version of the Auslander algebras of type D also have some interpretation, but I don't know. Good, also very good question. Sounds like a very good student project. There's one more question. Is the paracyclic symmetry coming from the... Yes, that's exactly right. It's specific to stable, and it's not present in essentially any of the other models, any of the other categories. So. Presumably, stable categories embed inside paracyclic blah 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 2 Siegel objects more or less fully faithfully, something like this, right? So I don't know. So I don't have a proof of this, but I think it's
the Dyckerhoff conjecture.
Well, actually, I don't know. It's also something I think maybe Jacob Lurie may have asked me that too at some point. So it's maybe that. Yeah.
Okay, are there any more questions? If not, let's thank Toby again for a nice talk.